Welcome to the explainer. So, if you've ever held a piece of plastic, whether it's the sleek casing of the laptop you're using right now or just a simple water bottle, and actually wondered how it was built from the ground up, well, you are in the perfect place. Today, we're going to decode the invisible molecular world that builds the everyday materials all around us. Our main goal today? To really understand polymer synthesis methods and how those specific methods absolutely dictate the properties and applications of common plastics. And to do this, we're going to use a metaphor I'm sure you're super familiar with: Legos. Just as you can build a towering, complex castle from tiny individual plastic bricks, chemistry builds our modern world from tiny molecular blocks. All right, here's our game plan for today. We're going to cover 1. Overview of polymers, 2. Addition polymerization, 3. Condensation polymerization, 4. Polymer blends, and finally, 5. Applications of common plastics. Let's get into it. Kicking things off with Section 1, Overview of polymers, let's lay down our basic chemical foundation. So, to understand plastics, we really have to understand the polymer itself. By definition, polymers are macromolecules, meaning they are extremely large molecules. But obviously, they don't just magically appear out of thin air, right? They're formed by linking together much smaller, highly active units called monomers. Think back to our Lego metaphor for a second. A single monomer is basically a single Lego brick. On its own, it's just a small piece. But because it has active connection points, you can snap it together with another brick, and another, until you have a massive continuous structure. That resulting giant structure, that is our polymer. Moving right along to Section 2, Addition polymerization, where we'll see exactly how this molecular chain gets built. So the absolute crucial point here is that addition polymerization is literally what it sounds like. It's incredibly direct. For this to work, you need monomers that have at least 2 active functional groups. You can think of these as the sticky ends of the molecule. When the reaction triggers, these monomers link up end to end to directly form a really long macromolecular chain. And what's genuinely brilliant about this specific synthesis method is its efficiency. It generates 0 byproducts. Every single atom from the starting monomers gets incorporated right into the final polymer chain. It's like having perfectly fitted blocks that snap seamlessly together without leaving even a single speck of plastic dust behind. There's actually a massive variety of functional groups that make this snappy connection possible. You've got groups like alkene, featuring these carbon-to-carbon double bonds, or amine with its nitrogen-hydrogen structure. There are also esters, epoxies, the list goes on. These specific functional groups are the essential sticky ends of our molecular Lego pieces. Without these highly reactive groups, the monomers just wouldn't be able to grab onto each other to form the long chains that addition synthesis requires. But, addition isn't the only way to build a polymer. That brings us to Section 3, Condensation polymerization. So, what's the difference? It's actually a pretty stark contrast. As we just learned, addition synthesis is this super direct linking process with 0 byproducts. Condensation synthesis, however, is very much a step-by-step process. As the monomers link together to grow the chain, a chemical reaction happens that actually kicks out a secondary product. Basically, in order for 2 monomers to join up, they have to physically expel a smaller molecule just to make room for the new bond. To really picture this in action, let's think about the synthesis of phenol and formaldehyde, which creates a really tough plastic known as PF. As these molecules combine, they don't just quietly form the polymer. No, they literally eject water as a mandatory byproduct of the chain formation. 3 H2O molecules are produced right alongside the new structure. This right here is the absolute hallmark of condensation polymerization. Building up the chain strictly requires the constant squeezing out of these smaller molecules. And the final result of that condensation process is honestly wild. These specific molecules don't just form some simple, flexible, straight line. They interlock into a highly complex, rigid, 3-dimensional web. The phenol rings are bridged together incredibly tightly. It beautifully demonstrates how invisible, microscopic chemistry strictly dictates a material's physical structure in the real world. Because of this dense, cross-linked web formed during synthesis, phenol formaldehyde ends up being this unbelievably tough, heat-resistant material. But hey, what happens when a single type of synthesized polymer just isn't strong enough or flexible enough for what we need? Enter Section 4, Polymer Blends. Imagine distinct rows of different polymer chains just physically mixed side by side. Unlike the intense chemical synthesis we just talked about, blending doesn't actually alter the core chemistry of the individual chains at all. Instead, they are held tight together by secondary physical bonds. It's kind of like weaving 2 totally different types of thread together into a single fabric. The threads themselves don't chemically change, but the resulting fabric takes on the best properties of both. This is exactly how engineers create literal supermaterials. Take tough PVC, for instance. By physically blending plasticized flexible PVC with rigid PVC, engineers deliberately combine the flexibility of one with the structural strength of the other to completely overcome their individual flaws. Boom, problem solved. Other common industrial blends include PC mixed with PET or PC mixed with ABS. The whole goal here is to cherry-pick and merge materials to combine their absolute best properties, creating a specialized plastic tailor-made for some seriously demanding real-world applications. All right, now that we've mastered micro-level synthesis and blending, let's zoom way out to the macro world. In Section 5, Applications of Common Plastics. The synthesis methods we've just been exploring, they are the exact reason we have massive global commodities like polyethylene, polypropylene, polystyrene, PVC, and polycarbonate. Fun fact, polyethylene is so ubiquitous that it is actually the most widely produced plastic in the entire world. We're talking tens of millions of tons made every single year. And these aren't just obscure chemical names, right? They're the packaging that keeps your food fresh, the pipes delivering your water, the safety helmets you wear, and even life-saving medical devices. Understanding how they are synthesized from the ground up gives us the power to interpret why polycarbonate is tough enough for bulletproof glass, while polyethylene is flexible enough for a grocery bag. There's actually a fascinating historical perspective on this from Brightson's Plastics Materials. Speaking specifically about polypropylene, or PP, it notes that its post-World War II breakthrough is arguably the most important episode in polymer science history. And it makes sense. Before these advanced synthesis methods came along, man-made materials were structurally pretty crude compared to naturally occurring polymers. Mastering the architecture of materials like PP was a massive historical leap. We literally went from just using whatever crude structures nature gave us to these highly controlled, meticulously engineered synthetic powerhouses. A real game changer. Which brings us to the future. We've gone from the microscopic snapping of active functional groups all the way to the mass production of materials that quite literally define modern civilization. But the journey is far from over. The next great challenge is taking this deep understanding of polymer synthesis and applying it to our current environmental reality. So how will manipulating these invisible molecular chains shape the future of sustainable and advanced materials? How can we engineer the next generation of our molecular Lego blocks to be not just tough and useful, but truly circular and green? I'll leave you to think on that. Thank you so much for joining me on this explainer, and keep questioning the incredible science built into the world around you.